So, in continuation to my last lecture, I was talking about grain size distribution, and grain size distribution can be done by that is mechanical analysis. What I have mentioned, that is actually by using your sieve, and for sieve actually can be used for coarser particles, that is bigger than 75 micron, and if it is a smaller than 75 micron, we have to go for hydrometer analysis, and this combination finally you have to plot. And of course, most soil will have both, and sometime for this combined analysis, when it is silt and clay is present, very difficult to separate. So, what we do generally, we take some amount of soil and then wash through the 75 micron, and then when it will wash through 75 micron, then those finer than 75 micron the silt and clay will pass through, and then that will be collected and dried, and that dry sample will be taken for hydrometer analysis, and on 75 micron sieve whatever retained, that also can dried, and then it will be sieved through different sieve, and then the combined analysis will be done. And after combining analysis, we will be doing the plot, and then after plotting, by seeing the shape itself, I told you that if the S shape, then it is called well graded, that means all particles by and large present in the mass, that is well graded, it is good. And if the soil the curve is a very steep like the vertical like, that means in a particular size is present, that means uniform, that is also not good. And also some particles are present somewhere, some particles are not, that gap graded or poorly graded soil also can be there from the shape itself. But if the curve is smooth and still sometime we can do some calculation to classify the soil, that is one or such calculation is coefficient of uniformity or uniformity. That means that Cu is given by D60 by D10, you can see D60 by D10, and D60 is diameter corresponding to 60% passing. Similarly, D10 is the diameter of particles corresponding to 10% passing. So, these two quantity actually can be obtained from the curve, and you can find out the Cu. When you calculate this Cu, then the value one number you will get, and at the number the soil to be well graded, it has to be between 1 and 3, and if other than that, then it is not well graded. That is what we can decide. Similarly, coefficient of curvature, that is the equation is given Cc, so that is D30 square by D10 into D60. Here also from the curve itself these three quantities to be noted, and this can be calculated, you will get another number. And this number actually if I get, if it is greater than 4 generally is gravel, and greater than 6 generally it is sand. So, like that some qualitative information also from this number one can find out. So, this is about the grain size distribution and some calculation, and sorry. And as I have told that this is one sort of if the particles are bigger particles and no plasticity, those type of classification can be done. But if the soil contains mostly of your silt and clay, in that case sieving and all is difficult, and we have to do some other type of classification, and for that before doing that classification you have to understand some behavior, and for to understand that behavior that our past researchers did different ways to streamlining the things. One such step was that consistency limits. Atterbucks actually gave 3 limits actually, that is one is liquid limit, and that is your liquid limit, then that is another is plastic limit, and one more is a shrinkage limit. And generally fine grained soil will have these limits. More the fine particles, more will be the plastic in nature, and obviously we will have this liquid limit, plastic limit, shrinkage limit depending upon their composition. And this liquid limit is, what is liquid limit? As per definition, the boundary water, this limits, these three limits, this is called limit, liquid limit, plastic limit, shrinkage limit. Actually what it is nothing but water content. It is nothing but water content of the soil. What is water content actually? If I take a mass of soil, and that mass of soil, it can be completely dry, or it can be completely saturated, or it can be partly saturated or partly dry. But whatever may be the situation, if I take a mass, and on that mass actually I can find out what is the amount of water present and what is the amount of solid present. And this ratio, amount of weight, amount of water divided by amount of solid, this ratio is nothing but water content, and these limits are nothing but water content actually. The liquid limit means actually water content at liquid limit, and plastic limit means at water limit, water content at plastic limit, and shrinkage limit is what? Water content at shrinkage limit. That means all are nothing but water content. And what water content? That is liquid limit water content, plastic limit water content, shrinkage limit water content. And in the soil mechanics, this water content determination is a one very routine work. Most of the test whenever we do, always we require to find out water content, and for finding out the water content, generally we take a sample, and with sample in a particular can we take the weight, and then after taking the weight, and you keep in the oven for 24 hours in a particular temperature, and then the moisture will be evaporated obviously after 24 hours, and then we take the, after 24 hours after drying, that weight we take. After 24 hours, whatever weight you got, that weight is nothing but weight of the solid, and difference of first weight minus second weight is nothing but the moisture present in it. So, moisture present divided by solid is the moisture content or water content. That is the routine work we do for every experiment or test that has to be there. So, liquid limit, plastic limit, shrinkage limit is nothing but water content at different stages. So, consistency limits are there, limits at different stages. So, liquid limit, the boundary water content between the liquid state and the plastic state, and it is called liquid limit. And what is plastic limit? The boundary water content between the plastic state to semi solid state, that is plastic limit. And another is shrinkage limit, that is water content at which the soil reaches its minimum volume, keeping it fully saturated. That means, I will go to the next slide, that when the soil water suspension, when we keep it and water content start reducing, the soil water suspension will have certain volume, and then if the water evaporated, then amount of water evaporates, the same amount of volume will be reduced in the mass. This is the assumption, most soil will have that. Some soil will have there, it may not have, that is differently, it will not be applicable, but in general for understanding liquid limit, plastic limit, shrinkage limit, when there is soil water mass quite is it almost like liquid stage, and when water will be evaporated, then volume will be reduced. How much volume will be reduced? Volume of water evaporated. So, like that slowly it will be reduced, and every time the soil will be saturated. That means, water present in the voids sometime either just sufficient to fill up the voids or excess. When it is excess, that is almost liquid stage, and when it is just saturated, that is almost solid stage, but all voids are filled up with water. So, like that it will continue, that means, while water will be evaporate while evaporating of moisture, the volume will be reduced linearly. Up to certain stage that will be applicable, and it sometimes soil will be reached to its minimum volume, and if you further reduce the moisture, then further reduction of volume is not possible. So, that limit actually, that means the water content at which the soil reaches its minimum volume, keeping it fully saturated, that is called actually shrinkage limit. So, how to find out on all those things we will discuss later on in the subsequently. Right now, these are the qualitative definition of the 3 limits, and you see this is the one what I have qualitatively told in the previous slide while discussing the states of consistency. That means, you can see states of consistency of cohesive soil. You can see this is the one viscous liquid, that means soil and water. In the water actually, if you put excessive water, the viscous fluid like liquid like thing will be there, that will be in this zone. And on drying actually, that its volume, this side is its volume, initially suppose volume was here, on drying at this stage volume become this, at this stage volume become this, at stage volume become this, and at this stage whatever volume it reached, further reduction of moisture, the volume reduction is not, this volume is constant up beyond this. And you can see this side actually, this is moisture, more moisture, and this side is moisture is decreasing and this side is increasing. So, when I am going from this to this, that means moisture is reduced, from here to here this further reduction, from here to here further reduction, and from here actually we get 0. So, that means, this is as we have qualitatively defined that viscous, the boundary between this liquid stage to plastic solid, that is actually liquid limit, and this plastic solid to semi solid, that boundary water content. At this point whatever water content, at this point what is the water content, that is called liquid limit. That means, boundary between this state and this state, that water content is your liquid limit. Similarly, between boundary water content between this and this, that means, this is a plastic limit. Similarly, this is the water content which is called shrinkage limit. Why it is called shrinkage limit? Because it reached minimum volume, and also at this stage the soil is fully saturated, and if you reduce further moisture, no volume change. That means, at this stage its volume was fully occupied by the moisture. So, this is the one, that means, on drying volume changing, and at this stage your volume reached minimum volume is reaching with saturated condition, that is called shrinkage limit, and this is this 2 stage, that means, semi solid to plastic solid, that boundary water content is plastic limit, and the plastic solid to viscous liquid, that boundary water content is the liquid limit. So, these are all of course qualitative definition that but very difficult if without doing any experiment, we will not be able to find out the exact boundary, it is very difficult. So, because of that we have some mechanism to find out that boundaries. So, you can see also some qualitative behavior also at different stages, when it is a we have defined liquid limit. This is suppose water, a particular soil contains water content is WL, suppose that a particular soil water content is WL, which is less than plastic limit. So, water content is less than plastic limit, the stress strain behavior will be something like this, because suddenly it will be brittle, it will break suddenly. So, shrinkage limit to this is called brittle solid, and if your water content WL is close to is equal to plastic limit, then we will get a curve like that, smooth curve, and then suddenly like that. And if it is a liquid limit, water content is equal to liquid limit, that means, if you take a mass and its water content is same as the liquid limit of the soil, then you will not get much strength, actually strain will be more with lesser stress. Whereas, if it is a water content is less than plastic limit, it will be straining very less with very high stress. Here also, if it is a liquid limit is plastic equal to plastic limit, then straining is less, and also stress is compared to less, and if it is a close to liquid limit or liquid limit, then at very less stress the deformation will be, strain will be more. Similarly, if it is a in the mass its liquid limit is if the water content is equal to the liquid limit, then it is like liquid only, and if I apply force, it will not be able to take any force. Because of that, you can see there is no stress here, that means without increase any stress, the straining will be very high. So, it will not be able to take any load. So, that means at different stages, what will be the behavior of the soil, from this curve actually one can understand. So, like if I take a sample from this zone, then this type of behavior. If I take this one, then you will get this figure, and if I take at this, then we will get this one, and if I take the sample from here, then we will get this type of behavior. And okay. So, these are actually some behavior, actually expected behavior at different stages of water content. If the water content is close to liquid limit, that means we will get very low strength, and the water content is very close to plastic limit, we will have good strength. That is what here we want to explain through this slide. And now, as I have mentioned that liquid limit we have mentioned, that is qualitative definition, because the boundary between these two, but how to find out boundary, that for that actually our Contd developed a apparatus, that is called Contd apparatus, and it has a cup. On that cup actually you have to prepare a sample, soil mixed with some water, make a paste, and that paste, with that paste we can make a soil over here, this one, and then finally from there you have to cut a groove, that there is a particular grooving tool, it will have some dimension at the bottom, some dimension at the upper surface. It is like it is after cutting the groove, it looks like two slopes, one slope this side, another slope this side, is one embankment this side, another embankment this side. And after when this sample is ready, then there is a handle. Through that handle, nowadays of course motorized is there, through motor also you can do it. By handle actually you have to rotate, and when you will rotate that one, there is a mechanism, by complete rotation it will be lifted maximum by 1 centimeter and dropped. So, it will be doing, it is lifted like this and dropping on a particular base. So, while doing this, then the two sides, there is two embankments like this, it is there through grooving tool grooves, those slopes when there is impact will get, then they will be coming closer. And we have to note when these two sides closed by around 12-13 millimeter distance, that to be noted, that number to be noted. That means, how many numbers required to close 13 millimeter distance. Okay. So, that number, and then that is one data, that is number of blows, and observation is 13 millimeter distance they come closer. And third measurement what you have to do, you have to take a sample from here, and that sample finally that sample from here you have to collect for water content determination. Finally, what you will get, number of blows corresponding to water content and corresponding number of blows. So, we are doing this test, cutting a groove, doing the impact by blowing, and when it become 13 millimeter closed closer, they are coming closer 13 millimeter distance, then I am counting the number and taking some amount of soil for moisture content determination. So, after knowing the moisture content, then this become one data, moisture content versus number of blows. Like that I have to do 4-5 trials, and by definition actually water content exactly at which we can two sides of mass from two sides touch by 13 millimeter distance, when we will give able to, when we will require 25 blows. That means, if the water content is such, by 25 blows I can bring mass from both sides closer by 13 millimeter distance. So, that is the definition of liquid limit. So, if that is the definition, so I will not be able to do exactly how much quantity of water is required. So, I will add different amount of water and I will prepare different sample and do this test. So, I will get 4-5 data points, that means water content versus number of blows, like that, and like the suppose there are number of blows and those corresponding points are here plotted, and this is observed that is a good control test, and whatever data we get, and if you plot in a semi-log plot, that is number of blows this side and water content this side, then those points by and large come in a straight line. And you have 4-5 points, they are not exactly 25. While testing, we may not, none of the tests may not have 25 blows, it may have 18 blows, it may have 22 blows, it may have 35 blows, but you may not get 25 blows. 25 blows actually corresponding water is the water content is the liquid limit. But how I can get it? We can plot this, and from this plot I can fix here 25 blows and corresponding go to here, and from here we can find out what is the moisture content. That moisture content become liquid limit. So, if I have a soil, that soil I will take and some amount, and that soil has to be passed through 425 micron soil sieve, and then you mix with water, make a paste, and then put a sample here, cut the groove, then apply blows, and that blows should be 2 blows per second, and then you observe when it become when it is touching by 30 millimeter distance. When it is 30 millimeter, then you have stopped, and then record the number of blows and collect the sample for measurement of moisture content. So, the moisture content and number of blows, that become 1 point, like that 5 points like 1, 2, 3, 4, then maybe another. You plot in a semi-log plot, from here 25 blows corresponding to this project, and then corresponding water content, that become liquid limit. So, like that one can find out the liquid limit of soil. And similarly, plastic limit, actually plastic limit is also a very qualitative test, and this is actually you have to mix with water, some amount of soil, and then finally you have to roll, initially you have to make a roll, and then later on you have to in a glass plate, like this you can see here. This is the glass plate, on that glass plate this is the soil, this is the actually soil, on below this your fingers, very lightly you have to roll it, and roll, and when it will become too long and you have to see still you are able to roll, that means moisture present is much higher than the plastic limit. So, you have to remold it and again roll it, like that you have to continuously do it, and when we find that we are able to make approximately 3 millimeter diameter thread and about to crack, that means it reached to its plastic limit. So, when we are about to make 3 millimeter thread like this and it is some cracks are formed, that means it is a plastic state. This is a lot of experience is required, it is not so easy to do, though it is a very simple test. That means below your palm plate, glass plate, you are rolling it and trying to make it 3 millimeter thread. When it become exactly 3 millimeter and start cracking, that is the water content, that is plastic limit. Then what you will do? Immediately collect that and keep it in a container, put it and take weight, and then put it in the oven. Next day you take weight, and from there you get the water content, and that water content is nothing but plastic limit. So, that way one can find out the plastic limit, and so one we have got this is liquid limit procedure, this is the plastic limit, and then we can go for shrinkage limit, and this is a shrinkage limit test apparatus. You can see there will be Mercalli displacement method generally used, and this is called shrinkage dish. This is called this small container. You have to mix with soil, mix with water, and make sufficiently thin, and then this container will be filled up, level it properly, and then weight has to be taken, and after taking the weight you have to keep oven drying for 1 day, and then after whole day if it is kept for air, some water will be evaporated and it will become, if it is sinking soil, it will become smaller, or it will be semi solid and with less moisture content, and under that stage you have to you can put this one in the oven for complete drying. When it will completely dried, you will see the soil sample which was originally with entire occupying entire container, and you may see that 30-40% may be empty, become soil sample becomes smaller. And then that in the dry condition, what is the volume? That volume is important for calculation of shrinkage limit. So, how to find out this volume? By you can take the weight, what is the solid present, you can find out, and for finding out the volume, actually what we can do, we can by Markari displacement, because it is not a uniform shape, it may be down in the middle and raised in the edge. So, because of that irregular shape, it is very difficult to find out the volume by measurement. So, what we can do? We can do by Markari displacement. So, Markari displacement what? Actually in a container, a definite volume of container you can fill up with Markari, and then this soil sample can be kept on it, dry soil sample, and then this plate is there, this is with 3 pins, that through that pin on that touching on that soil sample and force it to immerse in the Markari. When it is fully immersed in the Markari, then some amount of Markari will be displaced, that amount of Markari, displaced amount of Markari to be collected and weight will be taken. And once we know the weight and density of the Markari is known, we can find out the weight divided by density volume. So, that volume of the soil can be obtained by this way. And moisture content can be obtained initially when it is full of the can, we could have taken the weight, and after drying you can take the weight, difference of that will be the moisture content. So, these things can be done. After doing all those things, we can take help of take help of this diagram to find out the shrinkage limit calculation. So, suppose the initial volume is this, initial volume was this, and it was suppose weight was W1, volume was V1, and after drying at suppose the shrinkage limit, this was the volume and this portion was water and this portion and this portion was solid, and after drying volume will not change. So, this become air which does not have any weight, and this becomes solid. So, ultimately you have to find out that water content at this stage. What is the water content at this? That is the shrinkage limit. So, I can find out this weight minus this weight, that is nothing but Ws. I can find out this minus this. If I do, then I get this water. So, this minus this gives you this water. Then how to find out this water? I can find out this volume. I can find out this volume. How to find out this volume? I know this volume, I know this volume. So, difference of these two will be the volume. So, that you can see V1 minus V2 is the difference of this much volume is V1 minus V2, if it is V1 and if it is V2. So, V1 minus V2 is the volume, and what was the this much volume, what was the weight? The water only was there. So, V1 minus V2 into gamma W was the weight of water in this zone initially. So, I have this minus this I have got, that means I have got entire water. Now, this minus this into gamma W, this much water. So, now if I do this minus this, I will get this water. So, by doing this, I am getting this water and divided by the weight of solid. So, water divided by solid, that is nothing but water content, and that is water content at shrinkage limit. So, this is the way we can find out the shrinkage limit. So, like this 3 limits one can find out, and after getting this liquid limit, plastic limit and shrinkage limit, we can we can get actually plastic limit this is one plasticity index IP, which is nothing but liquid limit minus plastic limit, and these are the notations actually the different places. Sometime we can say WL, sometime WP, LL, LP like that, PL like that we are used, but here WL, WP is nothing but liquid limit. This is WP means plastic limit. Difference of liquid limit and plastic limit is the plasticity index. Similarly, liquidity index, there is another natural water content minus plastic limit divided by IP is the IL, and relative consistency IC is the WL, that means liquid limit minus natural water content divided by IP is the IC. So, these are the different parameters one can find out after knowing liquid limit and plastic limit, and this can be utilized for classification purpose. And you can see the soil classification based on plasticity index. When plasticity is 0, then soil description is not plastic. Plasticity index, that is IP, is 0. That means, the soil may not have liquid. If it is sand, if I try to do liquid limit test, you will not get. So, that is actually non-plastic soil. So, you will get 0, sorry. So, 0. Similarly, if that plasticity index is less than 7, that soil is classified as low plastic. If it is between 7 to 17, 7 and 17, it is medium plastic. Greater than 17, that is highly plastic. And consistency of cohesive soil, that is consistency is liquid, description is liquid, IC value will be less than 1. I have just shown parameter IC and IL, liquidity index, and that is actually what are there. If this is the consistency, if these are the consistencies, if these are the consistencies, sorry, if these are the consistencies and this is the description of the material, then what is the value of IC expected, what is the IC value, or IC value if it is this, then what is the corresponding soil. So, like liquid less than 1 IC, IL will be greater than 1, very soft soil, then IC will become 0 to 25 and IL will be 0.75 and 1. Like that, if it is plastic soil, then stiff, then 0.751 is the IC and this one will be 0 to 0.25, and semi solid, this is plastic, this is semi solid, very stiff or hard, then the IC value will be greater than 1 and this will be less than 1, and solid, hard to very hard, and it will be also greater than 1. So, this is the classification. That means, if I know those values, liquid limit parameter, liquid limit, plastic limit, and single limit, of course, directly it is not coming in picture in this classification, but liquid limit, plastic limit and natural water content, then we can find out those IC and IL, and based on that, if I can classify what is the state of the soil, whether it is liquid state or very stiff soft soil or medium stiff soil or stiff soil or very stiff soil or hard or very hard soil. So, based on this we can classify them. Sorry. And this is another actually plasticity chart. That means, when the soil is plastic, that means, when the silt and clay is present, then when it is a granular soil, for classification purpose we have used that sieve and hydrometer, and you have plotted grain size distribution curve, from there some calculation and do the naming of the soil, and but where it is a fine grain soil, then this classification sometime not applicable, and instead fine grain soil, what you have to do? You have to do the consistency limit test, and once you get the consistency limit, then you have to, from the liquid limit and plastic limit, one can find out the plasticity index, which will be kept in this axis and liquid limit in this axis, and this is the plasticity chart called. And this plasticity chart, which has a different component, you can see from the line started from 20 water content, and sorry, and this was started from 20 and this equation of this line is P I equal to 0.73 liquid limit minus 20. And if this if particular soil, suppose you have calculated liquid limit actually 35 and plastic limit is 20, then plasticity index become 15. So, and liquid limit is 35. So, 35 somewhere here, 35 somewhere here and 15 somewhere here, that means the soil is coming somewhere here. So, what it indicates actually from this chart, actually if the point comes here, that means I can classify the soil, that means if the point comes above this line, that comes actually it is clay, and the soil comes below this line, it is actually silt. And again there are two vertical boundaries, one is here and one is here, another is here. If before this it falls in this zone, then it will be low plasticity, and if falls between this, that means in this zone, that is intermediate plasticity, and if it falls in this zone, that is high plasticity. And similarly, if the points comes below this, that is below this line, again whether it is in this zone or in this zone or in this zone, based on that soil will be classified the silt with low plasticity, intermediate plasticity and highly plastic. So, like that, that means the way we have classified the granular soil, that is grain size distribution, plot, do calculation and find out, name the soil. Here actually if you have the fine grain soil, do the consistency limit test, and then you know the liquid limit and plasticity limit, and then based on that the point you bring in this plasticity chart. Based on the presence of the point, location of the point, I can classify the soil as whether it is clay, silt, highly plastic or low plastic. Like that, suppose one soil plasticity and plastic limit test, if I plot and comes here, that means the soil is clay with high plasticity, and if it comes here, soil is silt with high plasticity. So, like that, this chart can be utilized for classification of fine grained soil.